Welcome to lecture 2. As in the lecture 1 we had discussed some basic fundamental concepts about the modeling, so we will continue to learn some more basic fundamentals about the regression modeling. So in the last lecture you had seen that I had taken an example of a simple line like as y is equal to mx plus c, right? And here I denoted that this x and y, they are your variables, and whereas here your m and c, they are the parameters, right. So in statistics we have an understanding, or there is a tradition that usually we try to express these variables by some alphabets or by some Latin letters, and whereas parameters are expressed in say Greek letters. So you will see that that we will try to express the variable something like here y, x and so on, whereas these parameters are usually denoted by here alpha, beta, gamma and so on. That is our common language of statistics. So now in case if I try to translate now this model y is equal to mx plus c in the language of statistics, then I can write down here my variable here as say here y, this intercept term c, this can be written as say beta 0, and this m can be written as say here beta 1 and say here x, right. So if you try to see, beta 0 has the same role as of here c, and beta 1 has the same role as of here m, and x and y remains the same. So now once I say that the model is known when beta 0 and beta 1 are known, at least in this case. Okay, well, this is a very elementary situation, and you will see later on, well, this is too simple for us, but at this moment this is very important to understand the basic concepts using these small examples, right. So if you try to see here, I am saying that y is my here output variable, and this x here is my here input variable. So this is a very simple situation. Well, in practice there are usually more than one input variables which affect the outcome variable. So now if you try to see, it is very natural to extend this simple equation to a more general situation. Why? Because in practice usually there are more than one independent variables which affect the outcome. So I can extend this equation here as say y is equal to beta 0 plus say here beta 1 x1 plus beta 2 x2 and plus here beta k xk, and we assume here that there are not one but there are k input variables say x1, x2, xk which are affecting the output variable here y. So I can say here that here this beta 0, beta 1 up to here beta k, they are the parameters of the model, right. Okay. Now I try to address another question. So now we come to this another simple concept to understand one more basic fundamental. So if I try to write down here two sentences, model generates data or data generates model, which one is correct? In the lecture 1 we had discussed that model is simply a mathematical relationship to express a phenomena which is happening in the nature, and as a statistician we have no authority and we don't change the phenomena, we simply observe the phenomena and we try to present a model. So obviously the first sentence, this is correct, that the model generates the data, and this second sentence, that the data generates a model, this is not correct, right. But what's not really happening? We want to know the parameters of a model. The parameters are unknown to us. So the question is this: how should we know them? Once I know the parameters, then the entire model is completely known to us. So I can say here that, for example, if I try to make a simple diagram, that this is here somewhere, this is the process. This process is happening, right? And there is a model which is describing this process. And when we try to observe the process, we try to collect the data. What do you understand by this sentence? For example, if I take a simple example of agricultural. Suppose we decide that there are, suppose 3 variables, say this here, quantity of fertilizer, say this irrigation level, and say quantity of seeds. These are the 3 variables we consider, and we assume that they are going to affect the yield of a crop. So now suppose I say that, okay, I try to use 1 kg of fertilizer and I put 20 centimeters of, say, irrigation, and I use 5 kg of yield, and based on that I try to observe some outcome of the yield. Say suppose I get 20 kg of yield. Right. Now I try to repeat this experiment again with some different values. For example, now I say I am using here 2 kg of fertilizer, and I try to use here 30 centimeters of irrigation, and suppose I use 7 kg of yield, and suppose now this time I get 30 kilograms of yield. So we try to conduct this type of experiment, and then we try to collect the data. And now my objective is that based on this set of data, I want to know the model. So here you are saying that the model is generating the data. But now what are we doing? We are trying to collect this type of observations, and we are trying to find out a mathematical relationship between outcome, which is the yield of a crop, and these 3 variables. So now if we try to observe, what are we doing? We are going in the opposite direction. The model generates the data, but we are trying to observe the data and we are trying to find out the model. So don't you think that we are going in the opposite direction? Answer is yes. And this is the advantage of regression analysis. Once I say, what is the meaning of regression? Or more general, if I say, what is the meaning of regress? This means to move in the backward direction. To move in the backward direction. Means what? Why are we moving in the backward direction? What I am trying to say, model generates the data, that is acceptable, that is the correct sentence, but now we are going in the backward direction. We are trying to observe the data and then we are trying to find out the model. So that is why this is called a regression analysis. We go in the opposite direction. We collect the data, and from that set of data we try to infer about the phenomena, and then we try to express it in the mathematical format. And whatever mathematical format we get, that is essentially a model. So now if I come on, say, another aspect, that say about model. There can be 2 types of model. One is here mathematical model, and others are statistical model. Right. Well, what is the difference between the two? one of an important difference between this mathematical model and statistical model is that they are usually exact in nature. And statistical model, they take care of random variation. And the problem with this random variation is that this variation is not in our control. Right. Can we take a very simple example to explain the difference between the interpretations of a mathematical model and a statistical model? Right. So, let me try to consider a simple equation, say here y is equal to 3x plus 2. And suppose I say that y is my yield of a crop, say in kilograms, and x is my here quantity of fertilizer, and that is also in kilograms. Now, suppose if I say, if I try to put here some values of here x and y, say here x and here y, so that's right. If I try to put here x equal to 1, I will get here y is equal to 3 into 1 plus 2, this is equal to here 5. Similarly, if I try to put here x equal to 2, I get here y equal to 8, and so on. And suppose if I try to put here x equal to 1000, then I get here y is equal to 3002. Right. So, now what is the mathematical interpretation? The mathematical interpretation says that once we are trying to use here 1 kg of fertilizer, then we will get exactly 5 kg of yield, no deviation from 5, exactly 5.00000, and so on. Similarly, if I try to use here 2 kilogram of yield, then I would get exactly 8 kilogram of fertilizer. And in case if I try to keep on increasing the quantity of fertilizer, say for example 1000 kilogram, then I will get exactly 3002 kilograms of yield. And from the mathematical point of view, I can say that y is an increasing function of here x. But is that really correct? Now, let us try to see the statistical interpretation. We know from our common experience that whenever we try to take a particular size of plot in which we try to put suppose 1 kg of fertilizer, there is no 100% guarantee that I will get exactly 5 kilogram of yield. But possibly what we mean by saying 5 kg of yield is that if I try to repeat the experiment several times, this means if I try to take the same size of plot and almost under similar condition, if I try to put suppose 1 kg of fertilizer every time, then sometime I will get a yield of say 5 kg, sometime 5.5 kg, sometime 4.5 kg, sometime 5.2 kg, sometime 4.8 kg, and so on. And once I try to take the average of all these values, that will be close to 5 kilogram. So similarly, if I say from the statistics point of view, if I try to use 2 kilogram of fertilizer, then on an average I will get here 8 kilogram of yield. But here comes a main difference. The mathematics says if you keep on increasing the quantity of fertilizer, the yield is going to continuously increase. But now here statistics comes into picture, and we use our common sense and we try to observe the phenomena, and we say, yes, the quantity of yield is going to increase as the quantity of fertilizer increases, but this happens only up to a certain extent. And if you try to increase the fertilizer beyond a certain limit, the entire crop will burnt up. So that is the main difference between a statistical interpretation of the data and a mathematical interpretation of the data. Please note that I am not criticizing either statistics or say mathematics, but I am trying to take a very simple example, and I am trying to explain that what is the difference between a statistical model and a mathematical model. Both of them have their own importance. right. Okay. So now we try to take up another concept in the model. So model can be linear or this can be non-linear. And you also have seen that model has two components. One is variable and another is parameter. So now the question is, when you would call a model to be a linear? When it is linear in parameters or linear in variables? That is the question. Right. So now here I would say this is the basic definition. A model is said to be linear when it is linear in parameters. Right. This is a very important definition. Right. So now just to illustrate it, let me try to take here some examples. Suppose if I take a model only in with one input variable, something like beta 0 plus here beta 1 x. What do you think? Here there are two parameters, this beta 0 and say beta 1, and both of them have got the power 1. Right. So this is going to be a linear model. Whereas if I try to take it here, suppose here beta 0 plus beta 1 square x. So now you can see here, although beta 0 has got a power 1, but beta 1 is a square quantity, so this is a non-linear model. So in say another example, if I try to write down here beta 0 is equal to beta 1 say x square, then it is very simple. I can rewrite this model here as say beta 0 plus say beta 1 say x star, right, where x star is say this here x square. So this is again going to be a linear model. So this is a basic definition that you have to keep always in mind. Say in say another example, I can also write beta 0 plus beta 1 say here log of x. This is also a linear model. So this is what you have to keep in mind, that how do we define the a model to be linear or non-linear. Now our issue is this: we want to translate it into a proper definition. So if you try to observe over this or say these examples, so now we need to translate this definition into a proper way. So looking at these four equations, if you try to observe, in case if I write the partial derivative of the output y with respect to all the parameters, if this is independent of parameters, then model is linear. For example, if I try to write down here y is equal to beta 0 plus beta 1 x, you can see here that partial derivative of y with respect to beta 0, this is here 1, and partial derivative of y with respect to here beta 1, this is x, and both are independent of parameters, right. So now let me try to take here some examples. If I say y is equal to beta 0 plus beta 1 square x. Now in this case, partial derivative of y with respect to beta 0 is 1, but partial derivative of y with respect to beta 1, this is twice of beta 1 x, and this is a function of parameters, right. So in this case I can say this is a linear model, whereas in this case I can say that this is a non-linear model, right. Now let me try to take another simple example and let me try to explain how linear model can be converted into a nonlinear model. Suppose if I try to consider a function like beta 0, say x raised to the power of here beta 1. Well, obviously this is nonlinear. But in case if I try to take it here log on both the sides, then this becomes log of beta 0 plus beta 1 times here log of x. So this I can write down here beta 0 star, and this I can write down here say x star. So although I can see here that this is essentially a nonlinear model, so now we can see here that this becomes a linear model. But you have to keep in mind the parameters are now changed. This is a linear model in parameters, say here beta 0 star and beta 1. And now variables are also changed. Here you had here x, and now here your input variable is here x star. So this is one example where I have tried to show you that in case if we have a nonlinear model, possibly that can be converted into a linear model, and we can continue with our statistical tools which we try to develop for a linear model. Right. Okay. So now in this lecture 2 we have tried to consider some other basic elementary concepts related to the regression modeling. And in the next lecture, we will start with a simple linear regression model. Right. Till then, goodbye.